All right, so in the AI world, we've got this huge challenge, right? How do you teach a machine to understand the world as it actually is? This giant, messy, interconnected web of data. Well, today we're going to pull back the curtain on exactly how that's done.
Seriously, just think about it for a second. Your life isn't a clean little spreadsheet, is it? Nope. It's this massive, sprawling network. You've got your friends on social media, the traffic patterns in your city, even the crazy complex dance of proteins inside your own body. It's all connected. So the big question is, how on earth do you get an AI to grasp all of that?
The answer, it turns out, is a really cool piece of tech called a graph convolutional network. You'll hear it called a GCN. And this is a total game changer because it's an AI that's built from the ground up to think in networks, not just in lists of numbers.
So what's the big deal about GCNs? Well, they actually embrace the messiness of real-world data. They don't try to force everything into a neat little table. And because of that, they can see the context, the relationships, all the juicy stuff that other AI models just completely miss.
And look, this isn't some far-off futuristic idea. This is happening right now. GCNs are out there in the wild predicting traffic jams before you hit them, powering the recommendation engines that know exactly what movie you want to watch next, and even helping scientists find new life-saving medicines. It's pretty amazing.
Okay, but it wasn't all smooth sailing. There was a huge catch. As these data graphs got bigger and bigger, we're talking internet scale, a massive problem popped up. A bottleneck so bad it almost kept GCNs from ever leaving the lab.
See, the first way people tried to train these things was called full batch training, and yeah, it's as bad as it sounds. For the model to make one tiny little update, it had to look at the entire graph. Every person, every connection, all at once. The analogy here is perfect. It's like trying to read every single book in the Library of Congress just to figure out the meaning of one sentence. It's completely impractical. So yeah, this method was a total dead end. It was incredibly slow, and it needed a ridiculous amount of memory and computing power. Just impossible for real-world graphs. If GCNs were ever going to be useful, something had to change, and fast. And the solution wasn't what you might think. It wasn't about building bigger, badder computers. It was about being smarter. The breakthrough came from a really elegant idea, a classic technique from statistics, sampling.
The idea is actually super intuitive. Let's use an analogy. Imagine your giant graph is a huge pot of soup. Now, you don't need to chug the entire pot to check the seasoning, right? Of course not. You just stir it up and taste a single spoonful. That's it. In the world of GCNs, that spoonful is a small, cleverly picked sample of the graph. We call it a mini batch.
Okay, but hold on. You're probably thinking, how can one tiny sample possibly tell you anything about a gigantic, complex network? It's a fair question, and the answer is pretty fascinating. It all comes down to a core principle of how connected data works.
Basically, it boils down to this. Things that are connected are usually similar. Birds of a feather flock together, right? You probably share interests with your close friends. In biology, proteins that are connected in a network often perform similar jobs. And that is the secret sauce that makes sampling so effective. If you look at a small connected neighborhood, you can get a really good idea of what the rest of the network is like.
So, if we're tasting the soup, how do you pick the right spoonful? This is where it gets really clever. Scientists have come up with a few different strategies for sampling a graph, and each one has its own special trick.
Let's start with the first and maybe the most straightforward method. It's called node-wise sampling, and just like the name says, it's all about focusing on individual nodes, one at a time.
So how's it work? Well, let's say the AI is learning about one person in a social network. With node-wise sampling, you just tell it to grab a few of that person's direct friends to learn from. That's it. It's a super simple, direct way to chop a huge problem down into manageable little chunks.
But there's a problem. What if that one person is an influencer with like 1 million friends? Node-wise sampling would explode. It just doesn't scale well. And that's exactly why we have the next method, layer-wise sampling. This one is a bit more strategic. Instead of chasing connections down a rabbit hole, layer-wise sampling is like taking a snapshot of different levels of the network. This is brilliant because it stops that neighbor explosion problem dead in its tracks. You're no longer trying to analyze half of Facebook just to learn about one person. It's way more efficient. All right, on to our third strategy. This one takes a completely different tack. Instead of looking at single nodes or layers of the network, it asks, what if we just grab a whole intact community? And that's exactly what subgraph-based sampling does.
The whole point here is to keep the rich, local structure of the data. By grabbing a whole little chunk, like a department at a company, the AI doesn't just learn about individuals, it learns how they all connect and interact as a group. It's a really powerful idea.
So, after all that, which one's the best? Well, surprise, surprise, there's no single right answer. It's all about trade-offs. If you just need something simple and quick, NodeWise is great. If you're dealing with a massive graph and you're worried about it blowing up, LayerWise is your best bet. And if preserving those tight-knit community structures is what really matters, you go with subgraph-based. It's all about picking the right tool for your specific problem.
Okay, so we've been geeking out about sampling methods, but why should you care? What's the big picture here? Well, it's simple. Without these sampling techniques, GCNs would still be stuck in the lab. This is what makes them work in the real world.
Honestly, you can think of it like this. A GCN without sampling is like a Ferrari with an empty gas tank. It looks impressive, but it's not going anywhere. Sampling is the fuel. It's what lets these powerful models actually get on the road and tackle the massive data problems we have today. And you interact with this stuff every single day, probably without even realizing it. You know those product recommendations that are just a little too good? That's graph sampling at work. The way your social media feed weeds out spam and fake accounts? Yep, that's sampling too. It is literally the invisible engine driving so much of the modern web. So when you boil it all down, the story of graph sampling is about a really crucial lesson for the future of AI. It's not always about having the most raw horsepower. It's about being smart, being efficient. And by figuring out how to work smarter with data, not just harder, we've unlocked a whole new frontier of what's possible. So I'll leave you with this question. Now that we have this incredibly efficient power, what huge problem are you going to solve with it?